this point too much, but another figure from the book, that there's a really rich tradition of looking at this connection between dance and acting. Laban was definitely the most vocal advocate of the idea that dance and acting emerged from the same root. But if you look at these names, this is a very, again, illustrious history of this thinking: Meyerhold, Lecoq, Chekhov, etc. And since language has come already to this conference, there's a whole category of theories about the origins of language, so-called gestural models. And so these propose that before we spoke, we engaged in symbolic forms of gesturing. These are basically forms of pantomime. So when you bring in things like pantomime and mimicry and imitation, we're fairly close to dance. And so I think dance will have a role in future discussions of the origins of language. Going back to the table of contents. So the dance chapter is part of a section called the coordinative arts. So I talk about the arts of interpersonal coordination. I use the term coordinator for that. And so the other chapter in the same section is about music. And so if you look at the subtitles, this is really my take, my sense of the relationship between music and dance. The dance is about the coordination of bodies, and music is about the coordination of voices. And there are really strong, striking parallels between music and dance at all different levels. In the same way that we talk about, movement patterns in dance, we talk about melodic patterns and melodic motion in music. As mentioned, in the same way that dance has connection to semantic function via pantomime gesture, vocal music has it via speech and language. So very deep connections between them. And when I was working on the book, I was trying to research this topic about the choreo-musical relationship, and I found that there was very, very little. It's come up in all the talks so far. People have talked about this choreo-musical relationship, but as far as a formal study, it's actually quite an impoverished area of scholarship. But if you look at the way the dance theorists think about the structure of dance, it's totally parallel to the way that music psychologists think about the hierarchical structure of music in terms of some basic unit, in this case called the kaining, and then kind of a combinatorial buildup towards larger structures. And these terms are not mine. These are dance theorist terms that talk about motives and phrases. And so when we talk about choreo-musical relationships, for example, choreographing dance onto music, it's often something at this phrase level of the dance's phrase level, which gets aligned onto the phrase level of music. But this is a very understudied area of scholarship. Then my last intro slide before I go into the neuroscience. Here's my current pet theory that I'm developing and writing about. I call this a dual cohesion model, and that humans have evolved essentially two different ways of engaging in coordination in order to enhance social cohesion. And so I bring it up because dance is one of these two in my dual model, and the other one is conversation. So group dancing, just like through coursing, is our means of achieving coordination via synchrony, whereas conversation is the other way of doing it via alternation and exchange. And in support of these differences in these formats, we employ metric rhythms when it comes to coordinating through synchrony, and we use non-metric rhythms when we coordinate through alternation. So that's kind of the background. I'm going to now switch to the neuroscience. And I'm sorry, I need water. So it's nearly 20 years since I started this study. It got published 2005, 2006, but I actually started working on this, I think, 2003. And so this is the first brain imaging study of neural basis of dance-like movements, movements of legs to music in a brain scanner. And to the best of my knowledge, correct me, I think you guys know more about this than I do right now. I think it's still the only study. I think it's the first, I think it's the last, the last attempt that people made to look at the neural basis of dance. So I think, as far as I know, it's a standalone study.
We have one.
You do?
Yeah.
Okay.
Based on the.
Is it published?
Yeah.
Okay. One of the things about this unification thing is that I work in 10 fields and I'm just ignorant in every field now. And I've talked about this with
That's why we are here together, because that has been a challenge.
Okay, no, I'm happy to, I'm ignorant in it's terrible in every field that I work in right now. So, so this study looked at both the patterning and pacing aspects among these four Ps of dance. And so we looked at three different aspects, three really fundamental aspects about dance. First, the spatial patterning of dance movements, movement through space. Second, the metricality of dance. And third, it's been talked about quite a bit this morning, the fact that dance movements are often entrained, not always, but often entrained to musical beats. And so the participants were amateur Argentine tango dancers. So people like a lot of us who work day jobs and then in the evenings go out to Milonga and dance. But these were not professional dancers by any means, but just competent amateurs, like I think a lot of us in the room when it comes to dance in general. And so I taught them a basic box step that was reminiscent of the basic step, the salida básica of Argentine tango. So that they came in a week before the scan and I trained them how to do this movement pattern. And so here's one of our subjects that you can see. Okay, yeah. So this is the PET scanner. You can see the person's feet are placed onto a surface, a flat surface, which is inclined roughly 45 degrees. And this is what they did in the scanner. So this is the most basic condition that people engaged in the study. We call this the metric dance condition. Let me do something. Let me do something first. Okay, so then another condition is called the non-metric dance condition, and they performed exactly the same box step, and the mean tempo was the same, roughly 1 hertz, but now we played with the duration values to make the music feel very irregular to the dancers, and so it looks something like this. Okay, let me do this. I don't want to blast you. That's like on hallucinogen or something. I don't know what's going on there, but okay, so that will be called the non-metric dance condition. So first, I'm just going to summarize the results very briefly. So to look at the sort of the navigation aspect, moving your limbs, moving your body throughout space, we contrasted video number 1, the metric dance condition, with another condition called contractions. And here people simply had to contract the same muscle groups, for example, their glutes, their hamstrings, but to not move their feet along the surface. So this controlled for the muscle contraction, but there was no translation, there was no spatial navigation along the surface. And so the contrast should reveal areas involved in spatial navigation. So I'm going to show this contrast, metric minus contractions, and I see the repositories here, so now I'm going to make a comment that maybe you'll appreciate. Before I talk about the results, nowadays when you see brain images, the anatomical scan is not a single brain, very crisp and whatever. Back in these days, we took the average of all our subjects and we blurred them together into a single composite. And so when I look at these now, 15 years later, they look so ugly to me compared to the beautiful slices you see now. Anyways, this was the average of all our subjects. That's why it looks very blurry and pixelated. Anyways, the contrast between the metric dance condition and simply contracting the same muscles gave activations in a part of the brain that's very strongly associated with spatial cognition, the superior parietal cortex, Broadman areas 5 and 7. And this is a part of the brain that's typically associated with visual guidance of motion, but there's nothing visual in the study because the eyes are closed throughout. So this is all based on kinesthetic guidance of the limb, but pretty much the same area that's involved in visual guidance of limb movement. To look at the metricality of dance, we compared video 1 with video 2. So video 1, the beat was regular and predictable, and the second beat, again, the mean tempo is the same, but now there's not that sense about a pulse and regularity. So here are the 2 scans on their own. I just want to point out that most of what you're seeing here is simply auditory cortex. So much of the scan, you're just looking at auditory areas. So I'm going to have you focus on where I have the arrows. So if you look at the metric condition on its own, what you see is bilateral activations in one of the two major input structures of the basal ganglia called putamen. And so we see the bilateral activations there. When people do, again, this is exactly the same motor pattern, same mean tempo, but we've lost the metricality. We see bilateral reductions in the putamen, and then an associated increase in the output structure of the basal ganglia, which is the ventral thalamus, which gives us some indication about which of the two pathways of the basal ganglia is implicated in this effect. I just want to point out that, you know, this paper's been cited quite a bit by the Dance for Parkinson's people. When I did this study, this really wasn't a thing. I think it was just starting around the same time as when I was in the study, but people cite this study for the fact that, you know, doing these kinds of regular movements through dance can activate the putamen bilaterally, which is trying to recover this kind of a function in the case of Parkinson's. So finally, look at the entrainment aspect of dance. We compared video number 1, in which the movement's externally paced, to music, to another condition that we just called the motor condition, which people simply performed the movements without music, just self-paced. So there's no entrainment to a beat here, and here this is paced, this is entrained to the beat of music. And so the contrast should reveal areas involved in audio motor entrainment. I just want to point out a trivial difference between the two is that this one has music, this one doesn't. So we see auditory activations there, but not there. I'm not going to show that. The biggest difference between these two conditions outside of the auditory cortex was found in the cerebellum, but not in the hemispheres, but instead in the midline, the vermis of the cerebellum. This was kind of our marker for audiomotor entrainment. And then several years later, we decided to do a meta-analysis of up to the time, the entire finger tapping literature that had been published up till 2014, with an eye for the same kind of contrast. And so if you look at red, again, this is across 30-something studies, but if you look at red, these are brain areas that are more active when people have to do paced finger tapping compared to self-paced finger tapping. And again, we see just two areas. One is auditory, which I think is sort of trivial, but then the other area outside of auditory cortex is the vermis of the cerebellum. The basal ganglia was shown to be more active during self-paced than externally paced. The cerebellum is kind of the marker for externally paced audiomotor entrainment in this study. So just to summarize this study, spatial patterning, navigation of the limbs during dance was associated with circuits in the superior parietal cortex, the metricality of dance associated with the putamen of the basal ganglia, and then entrainment of dance movements to an auditory beat associated with the vermis of the cerebellum. And so this study was nice first, not last, okay, so I guess it wasn't last, but first attempt at dance. But of course, we all know the phrase takes two to tango. And so what was missing was this interaction, the partnership between two people. And so we did a follow-up study, far and away my most difficult. I never thought I would actually get to the point of publishing this. It was so complicated, but looking at two-person interaction, haptic interaction, and looking at leaders versus followers. So this one's going to look at another P, the partnering P of dance. Again, we took experienced couple dancers. This was many years later, a different city, the whole thing. But again, we took experienced couple dancers, including tango, salsa, ballroom, as long as people had experience with couple dances. And so the main thing to look now is at the difference in the brain between what does it mean to be a leader versus a follower. I think a lot of us do couple dances and say, oh, that's really similar, but they're different worlds as far as the actual execution. And so to be a good leader, a leader technically is someone who plans and initiates the joint action. If there's movement, the person who navigates, think about a tour guide, who's going to take a tour. And if there's haptic interaction, this is the person who conveys forces to the other person. To be a good follower is exactly the opposite profile. To be a good follower, you want to be really responsive to these force and navigational cues coming from your partner, and essentially be tracking these cues from the leader. And just briefly, I'm going to go off script. I always tell my students the story about the best follower I ever interacted with. And so one year I was on vacation. It happened to be Mallorca in Spain. And I was walking out of my hotel to go to dinner at a restaurant. And I came to this very busy intersection. And I don't know how this guy was here, but there was a man starts talking to me, and he says he's blind. Could I help him get across the street? again, I don't know how we got there or whatever. That's not part of the story, but I was very nervous. I didn't want I didn't want to do it because this intersection was so busy. It was going to be hard enough for me to get across the street without putting someone else's life, in danger. So I was really hesitant. I said, "What do you want me to do?" He said, "Put out your arm. I'm going to grasp your arm. We're going to walk together." I was very hesitant, but I did it. And we start to walk. And within 20 seconds, all my fears melted. This was the best follower I ever interacted with. This guy was so exquisitely sensitive to every cue that I was putting out there. I had nothing to worry about after a few seconds. So I talk about this man being the best follower that I ever danced with. And it's really, I think about that experience that way. So leaders and followers, this is a very complementary kind of role playing, but there's also a third condition where we do things as co-equals, where there's symmetry there, there's no leader, no followers. We also, in addition to looking at leading and following, we looked at what we call this more mutual kind of interaction. And so this photograph we made for promotion purposes, but it's totally bogus. So I need to correct what's going on here. So this is my graduate student. This is sort of me, my graduate student layout to the right. But this is not the way it actually happened, because when you go into an MRI scanner, you're pretty much up to your waist, and then your hands kind of stick out. And so in reality, the subject was inside the scanner, not outside the way it's shown here, with their hands kind of sticking out. And Leia was placed right there, directly next to the board of the scanner, interacting with the participant. It took us a full year of working with the MRI physicists to work out all this distortions. It was a really difficult study. I thought it wasn't going to go in the end, but the work paid off in the end. But anyways, so we had this direct haptic contact during MRI scanning. And so the two people engaged in improvisational bimanual interaction as shown here. So these kinds of wrist rotations, improvisation wrist rotations. So when the subject saw lead, then he or she led these movements and Leia was the follower. When they saw follow, Leia led the movements and the subject was the follower. So this is on the extent, but if you think about, there's an MRI here up until that point. So this is just in the lab. And then to look at the mutual, we just taught them a few fixed patterns that were quite similar to those involved in improvisation. So there was fixed pattern 1 and 2. They just got cued, do fixed pattern 1, fixed pattern 2, fixed pattern 3, but just very similar to the rotations that would occur when doing the improvisational movements. Okay, so this is basically a 2x2 design. So one dimension was whether the movements were either improvised as in leading following or pre-learned as a mutual. And then we decided to look at non-partner interaction as well. So in the solo condition, they improvised these movements, but they did it without a partner. And then in the alone condition, they were simply cued to do these fixed patterns, but again, without a partner. So again, keep in mind that as in the first study, there's no visual stimulation here, the eyes are closed. And so the first we looked at was just simply what's the effect of interacting with a partner, what's the main effect of partnership. So we compared partner conditions against the non-part conditions. And you can kind of imagine that if you're doing this compared to not, there's going to be lots of sensory stimulation. So not surprisingly, we see these huge activations in both the primary and secondary somatosensory cortices of S1 and S2, as well as sensory-motor parts of the insula, this motion tracking area, PSTS. The area that was really new for me from this analysis was this mid-cingulate cortex. We all know about anterior cingulate, posterior cingulate. I didn't know much about the mid-cingulate cortex, but it really fits the pattern here. This is an area that's involved in essentially haptic guidance of movement. And so it really fits the pattern for partnering kind of area. But of course, our motivation for the study was to look at the neural differences between leading and following. So let me focus on those differences among just the partnered conditions. So sometimes you do an experiment, you look inside the box, and you see results that more or less agree with your intuitions. And so looking at the results for leading, highly motoric patterns. So we see a bunch of areas involved in motor planning, like the premotor cortex, the SMA, I talked about this superior vital area for navigation in the first study, cingulate motor area, inferior frontal, cerebellum, so a highly motoric pattern for the process of leading. By contrast, if you look at following, it looks totally different and much more of a sensory profile. So as shown here in blue, we see the secondary somatosensory cortex, again, the PSTS, even the sensory part of the thalamus was activated during this. But this one was the biggest surprise. So I think a lot of you know this area called MT plus V5. It's the classic visual motion area. So if you have like dots, moving across the screen, V5 is the area that's activated by visual motion. And so you get this result, you say, oh, that's weird. But then you look back and yes, 20 years ago, someone showed that V5 is also responsive to haptic motion. So movement along the skin. You don't know this because it's like 3 papers that were published a long time ago. But in fact, V5 is also responsive to haptic motion, not just visual motion. And in other analyses, V5 turned out to be one of the best markers of what it means to be a follower from a neural standpoint. So surprising area given its association with visual activity. Again, no vision at all in the study. So those were the complementary roles. What about when it's something much more symmetric? So there's no improvisation, you're doing the same movements at the same time, very symmetric, co-equal. And so before I show you the results, we can kind of, in a Peter Keller kind of way, because I think about these kinds of issues all the time. So when you have this kind of co-equal thing, is that akin to 2 people leading each other? Or is it akin to 2 people following each other? So it's a mutual following. Or is it something, a third thing altogether? So here are the results for this kind of this mutual, these fixed pre-learned things. And as you can see, there's no red here. So there was no evidence that the mutual interaction was 2 people leading each other. There was some minimal evidence that there's mutual following. We saw an overlap between following and the mutual and the PSTS. But for the most part, we got a third pattern shown here in yellow. And it's a very interesting pattern in terms of cognitive science. So on the one hand, we've got a bunch of areas that are part of the mentalizing network. So the temporoparietal junction, the posterior cingulate cortex. So this is part of the brain involved in inferring. I guess Nikki kind of alluded to this morning. Actually, I'm sorry, talking about mental time travel, not mental mind travel. My mistake. Okay, so you didn't talk about this. But inferring the thoughts, beliefs, emotions of your partner, of another person. In addition, we see this really fun area. We have Robert Satori, he also, who knows the area well. The nucleus accumbens, one of the pleasure centers of the brain, along with the amygdala. And so this combination, this network of mentalizing plus nucleus accumbens, this is the network for cooperation. People show this is the pattern of cooperation. And so this kind of interaction, this mutual interaction, is definitely a cooperative form of interaction. So anyways, this is kind of a signature for cooperation in the literature. And so last, because they changed the name and all this, so I had to do something about creative movement, even though it wasn't, but it's part of the study anyway. So we definitely had the basis for comparing the conditions that were improvised versus those that were not. So we did the improvised versus non to get a sense of the neural basis of creative movement. So improvised versus non-improvised. And briefly, it's a pattern that looks very similar to the leader pattern. It's very dominated by motor planning areas like the SMA, PMC. But I also want to mention briefly that I recently published a meta-analysis that covers all the domains of improvisation. And so I cover all the domains that are available, that have been published. And so there's the study I just talked about, the mood study, but also creative verbalizing, musical improvisation, creative writing. These are the 5 domains for which there's published fMRI work. And the pattern was surprisingly reliable. 5 different domains, writing, drawing, whatever, but the patterns were surprisingly similar across domains. And here's the AL for the 5 domains, where the pre-SMA came out to be essentially the hotspot, the most concordant area of activation across all 5 domains of creativity, followed by other areas, other motor-ish areas like the premotor cortex, different parts of the inferior frontal gyrus, and the like. So very much a motor theory of improvisation, motor planning theory of improvisation. So to summarize the second study, again, looking inside the box kind of confirms a lot of intuitions that leading is dominated by motor processes and following by sensory processes. Doing the co-equal arrangement that's neither leading nor following gave us this network for cooperation. Again, the theory of mind network plus positive valence to the nucleus accumbens. And then, as I just mentioned, creativity is very much a sort of motor planning kind of story for that. Yeah, sorry. Yeah, I'm wrapping it up. So I talked about the 4 P's of dance. As I mentioned at the beginning, I think we need to, I've done work myself on, I've published stuff on pantomime, dramatic acting, but I haven't connected it with dance. So I think there's definitely a need to do that. They used to say, run, don't walk. You're like, run, don't walk to the bookstore to buy this. But what I realized in publishing a book like this, that I'm facing big hurdles. Everybody who works in the arts is really siloed in one arts domain. I get that. So if you work on dance, you probably don't think about literature and sculpture. And that's the obstacle that I face with a book like this. But when you buy the book, you'll go to page 23, and you'll see that I say here that a comparative analysis of the arts provides greater insight into each art form than is possible by looking at art forms in isolation. So comparison is the basis of all knowledge. I talked about the comparison between dance. I talked about conversation, music, theater. It's really important to have a broad and comparative approach. And that's what the book is all about. And that's it. Thank you.
Thank you so much for such an insightful talk. And we have like 6 minutes for questions and answers.
Oh, 6. Okay, I thought it was about 3 total. Okay,
No.
3 for me. Okay.
3 for you.
Okay, I was rushing to get. Yeah, that's fine. No problem. I'm here. Eric. Okay, Eric.
Oh, great.
I just want to say it was so hard to follow this morning, to come up here after this morning. I mean, it's just. I'm sick. I'm sick, but I would have felt really bad even if I were healthy, because it was just, you know, world famous choreographers and whatever. So, and Eric Jarvis. Okay, hi Eric.
Hi, how you doing? Good. So it was great to see this summary. And I'm like wondering, compared to things we discussed in the past about how closely opposed or adjacent or overlapping are brain areas involved in dance with brain areas involved in speech. And looking at the new things that you're presenting with partnering and so forth, I would say, if anything, it's that latest result of the creativity, of the improvisation, with the 844 and so forth. And I'm just wondering if I'm interpreting that correctly, and has your view changed over time?
I mean, so is your point about the 844 in particular, because this is very multimodal, right? I mean, so
yeah,
multi-factor, multimodal, so it's not specific to speech or any one thing.
Mm-hmm.
So.
But do you think that it was 3 areas, the 844?
For the creativity stuff.
Yeah, there it is.
Yeah.
SMA, the 844, and the curriculum as well. So these would be, your typical speech learning, speech production areas.
Yeah, but this
I'm wondering if they overlap with them, or are they adjacent, or what do you think?
This is a pattern for complex motor activity of any kind. So areas like the SMA, pre-SMA, whatever, premotor cortex. I mean, these areas you see here are found any kind of complex movement. I mean, I also want to point out, just to kind of side your question, but almost everything here was manual. So I mean, the vast majority of things. So there was one vocal study, but everything else was piano. So I mean, and this was the one thing that was vocal, but pretty much everything else, the drawing, writing, the movement, and almost all the music studies were manual. So that was a common link. Yeah, no, I think these areas come up, vocally and manually. So yeah.
All right, thanks.
I think that they're fairly domain general when it comes to that. And, there's some somatotopy in these areas, but they're general. I think. I'll let
In terms of the creative production across the 5 domains and looking at the areas of activation, one of the things that has struck me in looking at further studies of improvisation is actually areas of deactivation. Did you look for overlap in that? Because in some of the music studies, the study of lyrical improvisation, to me what was really interesting is apparent overlap in deactivation of prefrontal cortex. And in terms of thinking about automaticity and flow state and things like that, I'm interested in kind of the idea of not just what turns on, but what may be turning off. And I was wondering if you looked at that in your meta-analysis as well.
Yes, we did. So no, because it has to see were there sufficient number of studies. Because to do this kind of analysis, you need sort of 20 experiments in the same field. So there were definitely not 20 studies of deactivation for improvisation. There are a few, the ones that you cited, but not enough to meet the threshold for doing a valid AL analysis. We just kind of crossed the threshold for doing. That's why I had to combine things. Like I'd rather do. I'm sorry, if I had my way, I would do music by itself, whatever. I had to combine them because there weren't sufficient number of studies. You're kind of looking for a target like 18 studies, and there wasn't. So I had to combine them. It wasn't sort of my primary thing. If you look at the paper, you'll see that I went back afterwards and looked at the results of each paper and showed that this network was actually quite common. It didn't matter if you're doing writing or drawing, it was the same. So I kind of did this kind of unimodal thing post hoc, but there were enough papers to do what you're asking for. And I wish there were, because it's definitely an interesting story. And I can contrast the answer with Eric's that all stuff is kind of linked. I think is very domain specific as far as improvisation. The areas that come up for deactivation are much more domain general, so the working memory areas and all that. So it's kind of, the paper really contrast between is there domain specificity or generality for creativity. And so that's a big difference between the activation versus the activation stories, is where these activities occur. And the activations are much more in areas involved in non-creative. So whether you're doing creative drawing or not, these areas are important for non-creative drawing too. But these areas you're talking about are much more domain general, and deal with attention, working memory. You talk about flow, so it's a different category of areas that come up for the deactivations compared to the activations. So that's part of the story. But no, I couldn't do the AL on that. There's not enough studies. But great question.
I just wanted to say thank you, because your paper from 2006, the paper that you were discussing, is one of the reasons I got to do my dissertation with RGG Tango at Washington University with Gannon Earhart.
I know.
So, yeah, so that was really groundbreaking work, and thank you so much for doing that. and getting
Thank
that
you for
going.
saying that. Okay.
Don't get that off.
So you said that the mutual partnership or the co-equal involved the activation of the theory of mind network.
Yeah.
And I'm wondering why the like leading or following would theoretically not activate the theory of mind network, because you would imagine that, following and leading also involves inferring, maybe more so than co-equal partnership of thoughts, intentions, and beliefs, emotions, etc.
Good question. Yeah, and I thought about that too. And actually, I don't have the answer to that, but right now I have behavioral studies where we're actually trying to look at theory of mind. We're having people interact, and we interrupt them, and we put them in separate, what do you call them in Zoom, the rooms, the breakout rooms. And we ask people, what were you thinking? We just interrupt them. We say, okay, A, B, write down what were you thinking? And we're trying to understand what people do mentalize, and whether there is, like, I thought, yeah, that leaders, because I know as a dancer, I'm always mentalizing about my partner. In a reflective, like, what is she thinking of me? Is she impressed with what my move? That's what happens. I mean, sorry. Yeah, no, I agree that this came up much more in the mutual condition. Why is it not there in leading and all that? But I don't have the answer nearly, but we're trying to look at that actually right now in the lab in terms of what are people thinking when they interact with each other, and are they talking about themselves or talking about the partner or the topic of conversation? So I don't have the answer, but I've thought about this for years. So yeah.
Thank you.
Yeah.
So we have to move
Okay.
on. Thank you so
Thank
much.
you. Thank
again.
you.
Thank you.
Okay, I'll just leave it. Yeah, it's gonna.
So join me in welcoming our second speaker, Virginia Pillion from Concordia University in Montreal.
Thank you. Great. So I hope everybody can hear me properly. I am extremely pleased to be here today. I just want to get my timer going so that I can be as well behaved as all of the other speakers this morning. Good. So I am going to admit to having changed my talk title just a little bit. Now I'm really glad because of Tecumseh talking to us this morning about groove. So that means that I will fit right in. So what I'm going to talk to you about today are a couple of the studies that we've done. I come from more of a basic cognitive neuroscience background, studying motor learning, auditory motor integration, and particularly in the context of music. But I was lucky enough to do a study on dance. And then also we've been doing some studies about musical groove. So what I thought I could bring here today is to talk about what is it about dance. We know, and that you're going to hear more about the ways that dance interventions can improve gait and balance. They can produce changes in brain activity in Parkinson's disease. You're going to hear from Aga that they can produce changes in white matter in older adults. And there are probably other exciting studies that we'll hear about that I don't know about yet. But maybe what we don't know is how dance might produce these effects. Now, of course, we have ideas, and people who've done these studies certainly have ideas. We know that it's likely related to experience-dependent plasticity, right? So you practice, you change your brain. Engagement of sensory motor networks, that's clearly important. We want to think about the rewarding nature of the activity, and that's something that I'll talk about in the context of musical groove. And I think I won't really talk about this, but obviously Steve just talked about this. Peter's going to talk about it, but I think partner interactions are clearly very relevant. So what I'm going to start by talking to you about are some of the neural systems that are engaged by dance. And in a funny way, I could really just put up a big picture of the brain and say, these are the neural systems engaged by dance, right? But I'm going to break it down a little bit in terms of the systems that we're going to be coming back to later. So clearly there are sensory motor systems. There are the descending motor pathways that go from primary motor and sensory cortices down through the brainstem, activate the muscles, move the limbs. There are also the interhemispheric connections in the corpus callosum, which are important for coordinating movement on both sides of the body and controlling trunk. Now, those of you who come from a visual neuroscience domain will recognize this concept of dorsal and ventral pathways as coming from vision, but you'll forgive me, I'm an auditory motor neuroscientist, and so what I often think about is the auditory motor pathways, and in particular the dorsal stream that connects auditory information to motor and the inferior frontal region, so things like Broca's area and other action planning centers. The next set of circuits that I'll want to come back to are the cortical basal ganglia circuits. I was super happy to hear a whole discussion of these motor and basal ganglia interactions for movement and for synchronized movement. So what I'm going to help us think about is a schema in which there are perhaps three important basal ganglia motor pathways. One starting from the putamen, which connects to these primary motor and sensory regions. That is more about movement initiation, basic motor control. The pathways emanating from the caudate, which connect to premotor cortex, supplementary motor area, which are probably more important for things like planning sequencing. And then to talk about this reward nature of the stimuli, I'm going to think about the ventral striatum, including the nucleus accumbens, and its connection to medial and inferior frontal regions that are important for the evaluation of movement and movement outcome. The one region that I won't talk a lot about, but is one of my favorite brain regions of all time. I've done a lot of work on the cerebellum. If anybody wants to talk to me about it later, I think the cerebellum is key, but I'm not going to really talk about it today. So I'll start by talking to you about a study that I did with my late collaborator, Krista Hyde, and to her student, Felicia Carpati, who's right here, and my student, Chiara Giacosa. I was extremely lucky to be able to work with all three of these people because they all had dance background, which I do not have. So it was really terrific to work with them. And what question that we wanted to ask is, what are the brain structural consequences of long-term dance training? And rather than simply comparing this to people with no dance training generic controls, we thought, well, maybe we can get something out of comparing these people to musicians who also have long-term deliberate training in an auditory motor modality. So what we did is we compared dancers and musicians. These were contemporary dancers, so we didn't focus on ballet dancers, primarily because we wanted to have at least some representation of both males and females. There are just many fewer males in the ballet world, and harder to get your hands on those people. And then trained musicians. And we looked at brain structure in terms of changes in the cortical regions, but also in changes in the white matter, so the connections between regions. And we did some tests of musical abilities, which I'll show you that. And we also did a semi-test of dance abilities, which I know many dancers here will probably just hate, but you can tell me why you hate it and we'll discuss, but it's what we tried. So what we did is we had 3 groups. We had dancers, musicians, and controls. Controls were simply selected to not have dance or music experience. And what we did is we matched them. We matched them on their age. We matched them on their sex distribution. So there were still many more females than there were males. We matched them on body mass index. We thought this was really important. There's only one previous study looking at brain structural changes, comparing dancers to controls. And they saw reductions in typical measures of white matter connectivity. But they were looking at all female, all ballet dancers. And one thing that we know about female ballet dancers is they often have quite low BMIs. It's the aesthetic and the extensive physical training. And we also know from studies in people with eating disorders that BMI is related to white matter measures. So you can see in people with low BMI, low measures of white matter connectivity. So we wanted to be sure that any changes that we saw or comparisons that we saw between musicians and dancers weren't due to low body mass index in our dancer group. So body mass index was matched across the groups, and level of education was matched. Where we did match, and this is what we of course wanted to do, is that the dancers had an average of 15 years of dance training or experience, and little musical training, and the musicians had 15 plus years of musical training and very little dance training. And what we did with these people is we did a set of musical tasks. So there was melody discrimination and a control task, which I'll tell you in about 2 seconds. So in melody discrimination, as you might imagine, you hear a short melody, and I'll try to play that for you here. Come back. Sorry about that. So this is a melody. And then you have to hear it and tell me, is it the same or different? So the second one, different. And we had a control condition, which is that you've got a sequence of syllables. So something like ko-ru, ra, na, fu. And you either heard ko-ru, ra, na, fu, or you heard ko-ru, raya, fu. And you had to say same or different, and the idea is to control for auditory working memory. The second task that we did is a rhythm synchronization task. And what happens here is people hear a short musical rhythm, listen carefully, and then they hear it again, and they have to tap along in synchrony. So for example, this little rhythm here. So if you imagine, now I'm going to play it for you again, and you're going to try to tap along. Oh, sorry, I played the second one. Apologies. So they varied in their difficulty, and you just had to listen and tap along. And the third thing that we did is a dance type task. And what we used was the Dance Central video game. I think some of you may be familiar with this. It works with Xbox Connect. So what the person sees is a big screen, and they hear music and they see an avatar that is performing a dance-like sequence. I think for those of you who are real dancers, you might not consider this pretty plausibly. It's not really dance. You could think of it as kind of an aerobic exercise from the 80s, right? And the Xbox follows people's movement and gives you a score within the game of whether or not the movement was in the right direction and if the timing was correct. So I'll show you here one of our subjects. You can try to guess if it's a dancer or not. I'm going to turn the sound up. As I recall, this was a bit quiet. Yeah, here we go. Okay, you know what I'm going to do? I'm going to play you the second one because for some reason the clip is better in the second one, and then you'll hear the music. So you can see this one. So you can see, this is one of our non-dancer subjects, right? So she's not doing so bad, but she's following, right? And there's no smoothness. So if we go back to our first person who is our dancer, I think you'll see a real difference. And the hip action is definitely. So, as I said, while we're very clear that this is not dance in the sense of a creative movement that somebody would pay money to go see in a theater, this was a really great way for us to get a handle on people's ability, because we had as well ideas that maybe musicians, at least because they're used to synchronizing with other people and synchronizing with music, maybe they would actually be better at this than controls, although that is not what we saw. So what we saw was for the dance performance, hurrah, dancers perform much better than either musicians or controls, although musicians do perform a little bit better than controls. On the rhythm task, the musicians outperform both the dancers and the musicians. I realize this may seem counterintuitive. We think it has something to do with the fact that they're responding with their fingers, and that the level that we're asking them to imitate is really the metric level. It's item by item. It's not the whole sequence. And musicians also outperform everybody on the melody task. And another piece that I think that's important is that on that syllable sequence task, there's no difference. So it's not just a question of auditory working memory. So when we looked at brain structure, this is a whole brain analysis looking at dancers compared to controls, musicians compared to controls, and then dancers and musicians compared to controls in cortical thickness. So this is looking at the thickness of the cortical layer. So you can think about this as the thickness of the gray matter ribbon surrounding the cortex. And what you can see is that dancers differ from controls in this region of superior temporal gyrus and superior temporal sulcus. These are both high order auditory areas and sensory motor integration regions, so that bring together information from auditory visual senses as well. But these don't differ much between dancers and musicians. Really, the additional changes that you see are from musicians alone and not for dancers. when we look at the white matter, so these are the connections between different regions of the brain. What we found was evidence of reduced fractional anisotropy and greater radial diffusivity for aficionados of diffusion weighted imaging. What these measures tell us is that these reductions tell us that there's evidence for more dispersion, more fanning of fibers, or a greater number of crossing fibers. So when we talk sometimes about connections between brain regions, we think of them as if it's, my plug directly from one component of my computer to another component. But these pathways actually run in streams. They run along with each other, and there are multiple pathways. So what we're seeing here is evidence that in the corpus callosum, so this is this pale green region, in the descending motor pathways, so these pathways that send information from the brain to the body, and in the superior longitudinal fasciculus, so this is a pathway that connects more posterior sensory regions, so including visual, to these frontal motor output and motor planning regions. So what this suggests to us is that the connectivity is different, more dispersed, and that there may be greater connectivity, but because you've got greater connections in this dimension, and in this dimension, you're also seeing greater crossing fibers. And we were able to relate this to performance on that dance task, where you can see that an increased measure of this radial diffusivity is related to better dance performance across all three groups. So taken, the last part of this is that we then wanted to look at, well, what if we really look carefully at this descending motor pathway to see where the differences lie between musicians and dancers? What we saw generally replicate what we had seen in the previous study, but what we did is we traced from the trunk, leg, hand, and head regions of the primary motor cortex down through the pathway. And in musicians, we saw greater connectivity, so higher FA, which is evidence for greater coherence, so sort of that opposite in trunk and hand region. And the trunk we think is important here because it includes the shoulder and elbow. In the musicians, and in the dancers, we saw this, again, this pattern of reduced or greater fanning of fibers, greater diffusivity of fibers in almost all regions except the hand. So taken together, what we draw from this is that long-term training, so these are people with 15, 20 years worth of training, has an effect on pathways that are related to motor output and the intrahemispheric communication and sensory motor integration. And this is consistent, in fact, with studies in athletes and consistent with, I think, some of the work that Eva will talk about following dance intervention in older adults, excuse me. So of course, what we would like to think about, or what I perhaps invite you guys who are doing the intervention studies to think about, is that we might imagine that long-term effects might help us predict what we would expect to see with shorter term interventions, in the sense that we're not probably talking about highly specific changes related to one limb or one set of pathways, but perhaps rather more global changes. Now what I'm going to do is switch gears and hopefully wake you up by talking about this concept of musical groove, and by talking about this idea that Tecumseh really started with, which is this obligatory or very natural interaction between sound and movement. So this was a study that Robert and I actually did quite a number of years ago now with one of our first joint students and one of still our favorite students, Dr. Joyce Chen, who is now a professor in kinesiology at the University of Toronto, and she's very interested in interventions in the context of stroke. So what Joyce and we wanted to look at was this interaction between hearing and moving. So what she did is she had created these musical rhythms that we used in that dancer task for a different study. And what she did was she played them to people in the scanner, people who were not musicians, so who might not have an automatic association between hearing a rhythm and playing it in some way. And she didn't tell them that they would need to do anything. So just lie in the scanner, listen to these rhythms, and that's it. And the pattern of activity that we saw just during passive listening included the supplementary motor area, the premotor cortex. So these regions that are important for planning, for motor timing, and lobule 6 of the cerebellum, which is sort of a primary motor region within the cerebellum. And then what we did is we gave them a brief set of instructions, and we said, okay, now you're going to do the task that we've done before, which is you're going to listen to that rhythm, and then you're going to need to imitate it. And this is what we see when people tap along to that rhythm. So they're actually moving. You see enhancements in activity in the SMA, pre-SMA, and in the cerebellum. But you also now get motor output in the basal ganglia, right? Because you're actually making this action. And you get activity in this more supplementary lobule 8A of the cerebellum. So this is one of the first demonstrations of the idea that simply listening to musical rhythms could generate a pattern of brain activity that looks like movement. So that we wanted to link this to this concept of groove that I have to thank Tecumseh for introducing so much more elegantly than I could. And this is work that was done together with Maria Vitek, who's one of the godmothers of the study of groove, with Peter Voos in Aarhus, and my student Thomas Matthews, who's actually now a postdoc in Aarhus as well. And we jumped off work that Maria had done, but also Peter Janata had done, defining this concept of groove, and a little bit differently to what Tecumseh talked about, the way Peter has defined groove is the pleasurable desire to move to music. So it's not just that you want to move, it's that something about it generates pleasure. And I think many of us can imagine hearing Lady Marmalade or listening to Superstition by Stevie Wonder and just really wanting to move along. So what evidence might there be, or how would we generate hypotheses about where groove, or what would be the neural systems that would be engaged by groove? So there's sort of two streams of information that we put together. One are a series of elegant studies on beat perception that came from Jessica Grant's lab that showed that hearing a strong, predictable beat is associated with activity in the basal ganglia, but also in these motor regions, so premotor cortex, SMA, and obviously in auditory regions. And then I was also we were very much inspired by the work that my husband, Robert Satori, and his very brilliant student, Valerie Salamport, did, looking at brain response to the musical chills. So these pleasure responses to highly salient pieces of music for each of the listeners. So music that gave them the hair standing up on your head, shiver down the spine. And you can see that they saw activity in all of these subsections of the basal ganglia, so caudate, putamen, and most importantly, ventral striatum, that were related to this sensation of a strong emotional response. So what we did is to think about how we could create musical stimuli that varied in how much they generated this groove response, and that we could take into an fMRI study. So as Tecumseh talked about, one of the things that makes music groovy is syncopation, and Maria had done a study where she showed that this sensation of wanting to move and the sensation of ratings of pleasure are related to a moderate level of syncopation as opposed to either very, very simple meters or very complex ones. So I'll play you the stimuli that we generated. I'm also super happy because they were based on the Cuban clave. So since I had Tecumseh to explain all that, you'll recognize it right away. So this is a moderately complex version. We also varied the harmonic complexity to make them a little bit more musical. So here's moderate syncopation and moderate harmonic complexity. Sorry. And why not? Why? Oh, thank you. It's not bad, right? Like it's not terrible. And here is the more complex version. So it's more harmonically complex, so a bit more dissonant and also more metrically complex. So this sounds like you're trying to imitate New York City traffic or something like that, right? So what we did is we did an fMRI study. We had 29 musicians, 25 non-musicians. I'm not going to talk about musician, non-musician differences. There weren't that many. And we asked them to rate how much they wanted to move when they were listening to these and how much pleasure it gave them. And what you can see is that those moderately complex rhythms generated both greater wanting to move and greater pleasure, and that the harmonic complexity interacted only in the context of the pleasure ratings. And what we saw is if we simply contrast brain activity when you're listening to those high groove rhythms, so the moderate complexity versus the lower groove, you get activity in these motor regions, so SMA, pre-SMA, also parietal cortex, and the basal ganglia. But we suffered a lot because this basal ganglia activation that I'm showing you here's a big blob. It covers all of those regions that we were interested in. So what we did is we broke them down using an atlas into these regions and then looked at the relationship of the activity in those specific regions and the ratings. So what you can see here is that overall activity in ventral striatum, so this is this region that's much more related to emotional valence and response, is greater for the high groove rhythms. This is the only case where we got a modulation by harmonic complexity. So the harmonic complexity affects the pleasure ratings more or in the ventral striatum. And if we look at the relationship of activity in this region in relation to the rating scale, so you have pleasure with wanting to move co-varied, wanting to move and wanting to move with pleasure co-varied. This region is related both to wanting to move and pleasure. Whereas the putamen and caudate, we see the same global difference between high and low groove rhythms, but it's really much more related to the wanting to move aspect of the ratings. So what are the implications that I think for our findings? So we are showing you that trained dancers show more widespread connections in motor interhemispheric sensory motor pathways. It supports observed white matter changes following dance intervention and aging. In Parkinson's disease, it may be the case that training cortical networks, these networks that we're seeing are changed by long-term training, may support or bypass the deficient basal ganglia. One of the things that is, I think, a number of groups are looking at is whether or not musical groove, varying musical groove in the stimuli that you use could promote these intervention outcomes. So we've seen from our study that musical groove engages mirror and reward networks. We know that reward drives plasticity, right? So a more rewarding stimulus is going to drive greater plasticity. Behaviorally, a rewarding or pleasurable stimulus is going to drive engagement. So if you can get people engaged in this intervention, that may be very, or clearly is very important. And Parkinson's disease, high groove music may promote basal ganglia activity and also contribute to intervention effects. So I'll stop here. I'll really thank my collaborators. in particular Krista Hyde, who very sadly passed away 2 years ago. And I'll thank all of you, and I will look forward to taking your questions.
To read the script from Ara. Thank you, Dr. Penguin, and for your beautiful talk. Now we
How
have
did
5
she know?
minutes to take questions from the audience. It's actually 7. So I'm Aga.
Thank you, Aga, for assuming my talk would be beautiful. Yeah. Oh, sorry, the person with the,
Just
She
ask
had.
my question and give you the mic. So this is triggered by, in relation to the earlier talk, Steve's talk about leaders and followers and all that. So musicians are always leaders almost when they play the instrument and produce the music, whereas the dancer is always following the music. And I wonder how much do you control followers? Why is there some negative connotation with people follow? Can't go with that both if you don't have a follow.
So I'll say 2 things. First, Shihab got himself into big trouble right already. So I think many people would disagree with the concept that musicians are always leaders, because you can
With respect to
imagine.
the music they produce.
So,
I didn't mean to, for example. With respect to the music.
so I think, yes, it is the case that often musicians are producing the music that they know or read or whatever. So they are the effectors of the music, whereas you can think of dancers as following music, but that's not always the case, because dancers are doing many other things. There are many forms of dance where the dancer is not simply following the music, the dancer is interacting with musicians, and dancers are always interacting with other people, a huge component of dance. So I think, yes, in maybe some global sense, but no overall. So, yeah. Tecumseh, we're gonna go away, because then they'll pounce on you later.
Quick question about hemispheric asymmetry, and I'm just wondering
Yes,
if you
thank
saw
you.
some, because you might expect musicians to be more asymmetric than,
Yes.
than dancers.
So we did see, and you probably noted it, and I'm sorry I didn't say it, when we looked at the structural differences, we saw how interhemispheric asymmetry, actually both for dancers and musicians, more pronounced for dancers, where they showed the largest changes in right hemisphere, so the hemisphere that controls the left hand. For dancers, again, predominant on the right, but also changes on the left. So I think we can, all of the people that we selected for these studies, as in most brain imaging studies, are right-handed. So when you are a musician, what you need to probably train the most is controlling your non-dominant hand and bilateral control. For dancers, you are automatically training both sides of your body, but just as for the hand, people are footed. So people who are right-handed are typically also right-footed, and you need to train that opposite side of your body, and also because you're producing many more, not even symmetrical movements, but actually asymmetrical movements that require you to counterbalance the different components of the body. So we think that probably this right hemisphere effect is at least in part related to training non-dominant side, but it may also have to do with the fact that a lot of what you're training is related to auditory musical information, which we also know is has a right hemisphere predominance.
Yeah, I'm wondering, musicians, I'm assuming, especially since they're showing amplification of the hand area, if musicians are you separating out singers from instrumental musicians.
Yeah.
And I would imagine with singers, you might see something different.
So there have been studies that have looked specifically at singers and musicians. There are, of course, changes for singers in specifically in singing related regions of like the larynx and facial motor control. We don't control for that here.
So does that mean,
Because-
that means that the musician group does include singers?
It does probably, I would guess, in this sample, in most of our samples, there's like maybe one or two, because most singers are also instrumentalists. So getting a pure singer group, you usually need to, you want to compare that to somebody else, or you want to have a very homogeneous group to be able to really look at them. But one thing I will say, that I think your talk made me think a lot about it, is that one of the other things that we've thought about is that for most musicians, you're training your embouchure, your facial and tongue muscles, and your fingers, which are the effectors that have the most precise fine motor control and the largest number of muscles devoted to movements and the greatest degrees of freedom, right? So I think that there's probably something about that level of control that's very relevant. And I was really fascinated to hear your work related to songbirds, that you could think that there might be some sort of coevolution going on where your better control over your vocal motor system also promotes your use of that vocal motor system, and then they spill to other functionalities like fingers, right? And then that may provide a scaffold for some of the other types of movements as well, for using them in that very particular way. Yeah.
Okay, thank you. Yeah, I thanks for your talk. I really enjoyed it. I've thought there's like some of the questions that I have are around this sort of more general, around the sort of idea of dance as movement to music, and that some of those lack of differences and some of the large overlaps we see that has come from the fact that that captures only sort of perhaps a sort of small aspect of what dance is. I wonder if there's sort of if you could talk a little bit about like other ways in which dance expertise might manifest itself, like in terms of synergies or increased body interoceptive, or like those kind of, or even visual spatial capacities that might not have anything to do with auditory components at all. I was also thinking, just from personal experience, I know lots of dancers who are actually terrible at music and timekeeping.
Sure. Yeah.
Good dancers, but who have very little capacity to synchronize with music.
So I think what I would say is a lot of the times people are disturbed by the idea that we didn't see differences, cortical differences between the dancers and musicians, because, hey, we're dancers, right? We're special. So I would say to you, we saw incredible changes in huge connectivity patterns. So I might not think of it in terms of why aren't there differences in specific cortical regions that, in some intuitive way we think as being, that there's like special regions that are about being a dancer, that are trained by being a dancer. What I think is really even more exciting is to think about the connectivity changes. It's about the integration of sensory motor, motor, right? And many other things that seem to be, from our data, the results of long-term training. So I think you are also correct. There are many other things about being a dancer, and I think Lena Ting will talk about this afternoon in terms of actual motor control and motor kinematics and things like that, that we absolutely think would be different, right? Things that we didn't tap into with our relatively simple kinds of behavioral assays.
I'm sharing screen now, and I hope I can start. Okay. Hi, everyone. And again, I am so sorry not to be there in person. My name is Aga Burzyńska, and I'm assistant professor at Colorado State University. And I'll be presenting about the effects of dance on the brain and cognition. So in my laboratory, our main focus is to actually understand healthy brain aging and how it differs from pathological aging, such as Alzheimer's disease. And our particular interest is actually to understand how physical activity can help us maintain brain health and maybe postpone or even prevent cognitive impairment and dementia. So the question is how dance comes into this equation. Well, we all know that sticking to exercise routine is difficult, and the older we get, the more difficult it is to really meet the recommendations of moderate to vigorous physical activity. And especially when we think about scientific interventions, we also know that, for example, here on the bottom left, you see this how actually one of our interventions with aerobic walking looked like. And this basically looked like people making laps in a gym. And we observed that just making people do aerobic exercise to improve their aerobic capacity, it's not extremely motivating. And a lot of people just in general lack intrinsic motivation to stick to their exercise routine. So again, this is where the dance comes into play. So the wonderful thing about dance is that it is a physical activity. And also, if you recall session 1, we had some demonstration, and I could definitely see and hear increased breathing and heart rate of our presenters. But it also has elements of fun, of play, skill, learning. It provides us connection to others, as well as can be age and culture appropriate, because dance exists in every culture. This also means that we can always design intervention that is culturally appropriate. And furthermore, other research has shown that lifelong experience of dance training results in better preservation of cognitive and motor functions, and also lower incidence of dementia. This suggests that dance may have neuroprotective properties. And therefore, in our laboratory, for us, dance is a model of neuroplasticity. And neuroplasticity is a training or experience-induced changes in the brain that are adaptive and should result in better performance. So my talk, which is short, and this means that by now you are not more than 18 minutes from the coffee break. And as the talk was being prepared, I could see coffee carts moving in and out of the room. So my talk is divided into 2 main parts. First, I'll talk about a study in young professional dancers, where we looked into the cognitive and neuronal correlates of young professional dancers. And then I'll come back to interventions of dance in older amateurs. So in our study on young dancers, we hypothesized that the dance skill should transfer to broad cognitive abilities that can be measured in laboratory. We also expected changes in brain function, morphometry, and connectivity between dancers and non-dancers. And moreover, we expected that the dance skill should be correlated with those changes in the brain. So the first question was how to define dancers in a scientific way. And we interviewed several dancers from the UIUC dance department, and we decided for somewhat a range of criteria to define dancers. Well, first of all, we asked them, do you identify yourself as a dancer? Because we noticed that people who are really into dancing and they receive regular training, it's part of their identity. Then we also wanted our dancers to receive versatile training. And I'm grateful to Virginia, who already explained why we, for example, didn't want to have dancers that are only practicing ballet, because it may have some other implications, such as related to BMI and very, very strict training. And for our graduate students or more experienced dancers, we decided they have to have more than 10 years of experience. But for younger dancers, 3 years, but more than 10 hours per week should be sufficient. And our study was composed of only females to remove any sex-related variability in the brain. And also the ages were like 20 to 30. And our non-dancers had to report no history of dance training, including early childhood, but we did allow them for some casual participation and classes that may contain elements of martial arts, yoga, gymnastics, but less than 3 years and less than 2 hours per week, just because we did not want those two groups to differ on really physical fitness or activity. We really wanted them to differ on dance experience. And definitely those classes are offered at universities. So we recruited 20 dancers and 20 non-dancers, and both groups were matched on age, BMI, education, and fitness as we measured by the resting heart rate. And more importantly, our dancers, but not dancers, reported an average age of 6 of starting dance training and dance routine, on average 12 years of practice, of average 14 hours per week. So we managed to recruit sample that by self-report was definitely different on dance training experience. However, this is just the self-report. So we were looking into laboratory assessment of dance skill. And we were inspired by studies that Virginia mentioned, that we used the Dance Central. So you'll see how it looked in our experiment. So we kind of called it as a dance mimicry test. And what is important is that the Dance Central, the Xbox game, has been shown to have good to excellent correlation with better, more validated motion, like three-dimensional motion detection systems. So here you could see our dancer Angelica doing really good job at this dance mimicry. We also looked at balance as a skill that should differentiate dancers from non-dancers. And we invented this increased difficulty task, where, as you can see, our dancer is asked to stand on a foam pad on a dominant leg with actually eyes closed. And this was designed to decrease the ceiling effect, especially in dancers. So this is the balance task. So to cut the long story short, our dancers did outperform controls in both the dance game and the balance task. But what is also important is that the years of regular practice correlated with this Dance Central performance, which to us means that we maybe managed to assess dance skill in somewhat relevant way in our laboratory. So next, we were looking into what cognitive functions could benefit from dance training. So I went and observed several classes of dance in our dance department. And here you can see a teacher showing a sequence of motion that the students will be practicing to music on that day. And based on this, we thought that sequential memory, for example, tested by forward and backward digit span, could benefit from this learning of sequence, as well as spatial working memory, because you definitely see that dancers are moving in space, and relational memory for two reasons, because there's also some relationships in time, space, and different body parts, but also it's a physical activity. And we know that hippocampus, that's kind of responsible for relational memory, benefits from physical activity. And we also, like looking at the practice of dance, we could see that really visual processing of dance information seems to be critical. So we looked at the action observation network, which is a set of brain regions that is activated when we observe other humans perform motion, but we are not moving ourselves. And this concept of action observation network is extremely convenient to apply in MRI. And here you can see our dancer Angelica just starting her MRI experiment, because although the previous speaker showed how creatively they solved the issue of motion in a scanner, but the best quality of images are when we are not moving in the scanner. So the fMRI task that we designed involved viewing of clips of dance and control clips of animate motion. And when viewing dance, we ask participants to imagine that they are performing that motion. We just wanted them to be slightly more engaged. And by subtracting the control condition from the dance condition, we try to remove all brain activity that will be elicited by just observing motion, object recognition, motion detection, and so on. So here are two examples of those clips. And the dance clip, for example, we made sure that the body of the dancers were fully visible for the entire length of clip. We made sure that animal clips did not contain any emotional information, such as there was a giraffe walking, but she was not chased by a tiger or lion. And we also tried to make sure that the pace of those videos is comparable. So as expected, we managed to activate the action observation network in both groups, but we observed that action observation network was activated to a larger degree in dancers than in non-dancers. So in other words, they seem to be more trained in activating those brain regions that allow us to, analyze the motion that we have, that most likely also transfers to the better performance in dance mimicry. But this was about the magnitude of brain signal. We also wanted to look whether, the dancer's brain is wired in a different way. So are there any differences in functional connectivity? So how we calculate functional connectivity? We typically select two regions of the brain, we extract the time series, and we correlate them between each other in time to receive the kind of strength of the functional connectivity connection. And the results were pretty complex, but I'm really simplifying them here to show you that we found regions where dancers had stronger, like the pairs of regions where dancers had stronger functional connectivity between them, but also regions that had lower functional connectivity in dancers. But the important thing is that there was a consistent association of those functional connectivity differences with performance on the dance game. So the brain regions that showed greater functional connectivity in dancers, then this greater connectivity correlated with better performance. But in pairs of regions where dancers showed lower functional connectivity, then this lower functional connectivity was related to better performance. So this is the functional brain connectivity. We also looked into the white matter microstructure. And we found group differences in fractional isotropy in the posterior limb of the internal capsule, which is the corticospinal tract. So it is within the motor network. And again, what was especially important is that those structural properties of the corticospinal tract were correlated with functional connectivity in the motor network. Again, in this consistent direction that wherever there was a greater functional connectivity and which was related to better dance game performance, it was also correlated with, in our case, lower FA. And, Virginia mentioned how lower FA is somewhat troubling because we typically see lower FA as we grow older, but there are multiple reports showing actually lower FA in younger adults that is associated with better skill and training. So to sum up, so first I'll start with the negative findings that I did not describe just to save time. we actually found no evidence of cognitive transfer to other broad cognitive abilities. This means that our dancers showed not a different performance than the non-dancers on the tasks that I mentioned, as well as tasks of processing speed and general intelligence. We also observed no differences in cortical thickness or brain volumes. But we found that dancers express the action observation network to a larger degree than non-dancers, and there were also differences in functional connectivity in this network and in the motor learning network. And these differences in functional connectivity were as correlated with dance skill. And finally, also functional connectivity was associated with the measures of structural connectivity. So now I would like to move on and go back to amateur training in older adults. So we performed a clinical trial. The aim of this clinical trial was actually to increase levels of aerobic physical activity that should result in improvement of aerobic fitness that we know is beneficial for the brain and cognition. And this clinical trial involved randomization of over 240 people into 3 main intervention groups: the aerobic walking that you have seen before, active control, and dancing. And the important part here was that the active control was designed not to increase aerobic fitness. And our participants were between ages 60 and 80 years old. They were low active, but otherwise healthy, so they could undergo those exercises. And before and after the trial, we collected data on the cognitive ability and brain health. So here you'll see how the dance intervention looked like. So the key elements are that it is a physical activity, but it also involved learning of increasingly complex choreographies. And the intervention consisted of English country dance and contra dance to limit the lead-follow roles, which is actually related to the fact that in any kind of studies in older adults, we always have much more women than men. So we wanted to, limit any difficulty related to matching people in those typical dance pairs. And what we found using diffusion imaging, so the standard technique to investigate brain health, is that the integrity of white matter decreased over just 6 months in all of the participants, but improved in a dance group. And this was a localized effect in the fornix, and this structure connects the hippocampus and the limbic system. And it is also important in transition to Alzheimer's disease. And we are not sure exactly why we observed this effect only in the dance group in the fornix, but we speculate this is because dance is a combination of exercise, cognitive and social stimulation. And finally, using another technique, so a novel way to assess white matter integrity, we extended those previous findings. So here you see in the black is that the white matter health again decreased over 6 months in the control participants, but in the dancing and walking groups, it either increased, so the integrity improved, or declined to a lesser degree. So why is this result important? Well, for decades, white matter has been referred to as highways or cables of the brain. And this really suggests this passive infrastructure of the brain. But our study has shown that actually even the aging white matter is plastic. So we found plasticity induced by exercise and dance in the regions that are most vulnerable to aging. Therefore, we believe that dance and exercise are very promising as therapy. So why is this important? So looking at the website of National Institutes of Aging, and as most of you may know, there's still no drug that actually can improve the cognitive symptoms in cognitive impairment and dementia. and none of the medications can cure Alzheimer's disease. So we are now our only option is the prevention by maintaining of brain health for as long as possible. And my studies suggest that dance would be a good way to do it. So to summarize, we have shown that dance seems to have long-term effects on the adult brain in both younger and older adults, in both professional dancers and amateurs, although those effects differ. We found exciting structure, function, and skill correlations in the brain. And although we saw only limited effects on cognition, we believe that maybe we have to look closer into other cognitive tasks. And all in all, I think it is clear that to capture the complexity of dance with scientific methods, it's very challenging, and it calls for closer dancer-researcher collaborations. But all in all, dance, I would believe it's very promising for stimulating brain plasticity in especially older age. And our future work will aim to tease apart the cognitive, physical, and like social, emotional aspects of dance to also better understand the mechanisms and maybe dose response effect. So thank you very much. And here I wanted to give special credits for Art Kramer, who is there, and who was the PI of this clinical trial, and also Steve Drake, who produced all of the videos. Thank you very much.
Questions? People can ask it from here if you want, or you can repeat it. Yes. Or yes, or yeah. Or I
can combine it with
repeat
coffee break.
Okay, hold on. So you have some questions, so we finally figured this out.
Okay.
Just don't trip here. Yeah.
Yeah, it's probably not even worth coming up here, but thank you very much for the.
Let me get the question. Sorry. Yes, you can ask.
Okay, thank you very much for that. I had a question on the imagined dance, that you had more activity for the dancers than the non-dancers when they were imagining, when they were watching someone else dance, correct? Were you checking to see if their muscles while they were in the scanner were going? Like when they were imagining it, were they stretching their muscles? Were they moving any other activity that the dancers were doing that the non-dancers were not? That was my question.
Thank you very much. No, we did not check this, but this would be very interesting indeed. We actually instructed all of our participants, as always, for MRI to lie as still as possible. So I still may believe that the motion they were doing was minimal, but there's always some possibility that we did not check.
Can you hear me? Or I should go closer? Yeah. Okay.
Hi.
Can you hear me? Hi.
Yes.
Okay, so probably you will not have a specific answer because as far as I know, it has not been studied, but probably you will have, more of an informed opinion than I have. So I'm wondering, there is a lot of anecdotal information about, how someone can prevent cognitive aging. For example, people say you should pick up a new language. So even if I'm speaking English, which is not my native language, if I keep speaking it as I grow old, this doesn't count as preventing cognitive plasticity. It should be Russian or something that I don't speak. So would this be the same for different kinds of dancing? So if I'm dancing ballet my entire life, would I have to start dancing when I'm 50 or 60 or 70 salsa or jazz or something that I haven't danced in order to prevent cognitive aging? What would be your guess?
Thank you. It's a difficult question, but I think everybody wants to know it. Well, my personal take, also knowing that I do not only dance is just like my side expertise, if I can call it expertise, but I would say just a combination, I think, in a life of novelty, which can be sometimes just a social stimulation and physical activity and social activity. So I personally don't think that this has to be a new type of dance that we have to pick up later in life. I believe just engaging in even what you do, especially dance, always involves some learning, right? Because every partner, every music piece will be something new. That's kind of my personal take on it. That I don't think you have to pick up another form of a dance or language late in life.
Yes, all right, great presentation. So what I'm wondering, so when we are teaching, or when teachers are teaching somebody how to dance, it's usually best that they have their backs face the dancers, so they're copying the moves on the same sides of the body. And I noticed in the dance class, that's the way the teacher was doing it. But on your presentation and the presentation earlier, in the video games, the person in the video is facing them. So what they have to do is not only, they have to also they have to mirror that information in their brain in a different way than if they're facing the person's back. And I'm wondering if you thought about that, or even in the prior presentation, thought about that as to an extra cognitive load on the person who's doing the imitation, and whether that makes a difference also in the brain, looking at the back versus the front.
No, this is a great point. Thank you so much. And I really enjoyed your talk too. I mean, I must say we didn't perhaps think about this closely. All I can say that when I was a teenager and I did try to do a bit of modern dance, and I was not a trained dancer, it was extremely difficult to copy from a sequence like on one side to reverse it to the other, because a lot of dancers can just do it without the teacher showing them. But for me, I remember I always struggled with that transition. And, you know, I would say this is exactly what you're saying, that I'm not really so into dance as I should be to consider those things. That's why I think it's good to have more dancers and research. And I'm not gonna hide that Dance Central for us was a bit, you know, as an intermediate solution. We didn't have enough time and money and personnel. Like I ideally would like to have a dancer, you know, show people a sequence and then assess how they do it in some scale if it's possible, but it was just scientifically, given the logistics of the study, very difficult. So I definitely do agree that there is limitations to the Dance Central. And thank you so much for your comment. We should consider that in the future.
Yeah, something for the future, yes.
Yes.
Can I just say something regarding that? So, so in general, I think, you know, if as a dance teacher, you are taught to say, let's move the right arm.
Yeah.
Right? And so, and the dancers are also trained in front of the mirror. So they are used to mirroring. So dancers can do both. They can follow from behind, and they are very good at mirroring.
Yeah.
Exactly as a mirror. What is complicated and they usually don't do is that I move the right arm, they move the right arm. If I move the right arm, they move the left arm.
The teacher has to get very good.
The teacher,
Yeah.
that's instruction for trained teachers. You have to say, move the right
While moving left.
while moving the left.
Yeah.
So I always get them crossed because I taught a lot. So, but in the class, I'm very cognizant of saying, this is the right side, people. Yeah.
All right,
Okay.
good point.
Anybody?
Just to follow up to that, thanks for a very fascinating talk. What Eric said suggests another cognitive task that you might think about, namely mental rotation tasks. So, you know, where you have to say, are these two shapes the same with a rotation, or even can you identify the mirror image or something? So when you're thinking about the future cognitive tasks, you might throw in some sort of spatial manipulation task, because it suggests that
Thank you so much.
that's something that should be much.
We did actually have tasks of mental rotation, but we still did not observe any big differences.
Oh, well.
Well,
By my
any-
hypothesis.
but thank you so much.
Sorry?
I think everyone deserves a coffee break, perhaps.
Yes, okay, so let me, last one announcement that I want to, let everybody know before we forget. Tomorrow, Saturday and Sunday morning, from 7:45 to 8:45.
That's in the morning.
In the morning, you'll have the opportunity to experience the dance interventions that we're going to talk tomorrow in session 4 for Dance and Health. So Friday, it's Cristina Soriano and myself, and she has a creative dance intervention for cognitive decline. I'll be talking about using classical ballet for cerebral palsy and multiple sclerosis. That's tomorrow. Saturday morning, we have Peter Wayne that will be doing Tai Chi as a contrast of something that is movement sequences without music. And Sunday morning, we're going to have Lavinia Teixeira Machado that's coming from Brazil, and she does dance interventions for kids with autism. And Gregory Jordan, that is not here, but he does modern dance for Huntington's disease. Okay, so early in the morning, if you want to move, come with us. We'll be here somewhere. Where are we going to be?
That's going to be in the Ovations Pavilion where we were supposed to be today, which is just across the highway. When you exit, it's right there. There'll be signs, and it's the biggest pavilion. It's covered. There's no rain tomorrow. Just bring a little bit warm that time of day clothes. Yeah.
Okay, that's it. Coffee break.
Okay, so go have your coffee.